we have been talking about imposing complete binary trees on lists. Having done that, having studied that carefully, seen the consequences of that, basically the indexing between parent and the children nodes, let's impose one more condition. Let's say the value of the parent node, not the index, notice the value of the parent node must be less than or equal to the value of any of its children. If this condition is also satisfied, the tree that results is what we call a heap. Specifically, we call this a min heap because the value of the parent node is smaller than or equal to the value of any or say both of its children. In the same way, we can talk of something called a max heap. Well, the max heap, basically the idea is that the value of every parent node must be more than or greater. Basically, as we have been discussing, heaps are complete binary trees imposed onto a list of numbers. Remember the fact that it's a complete binary tree, which means filled from top to bottom, left to right. There is a very nice rule that emerges that for every parent node at index I, where this is zero-based indexing, so index I starts from 0, children are located at 2i plus 1 for the left child, 2i plus 2 for the right child. We spoke about this in detail, took several examples. When I take the converse of this, for a child node at index I, the parent is located at I minus 1, floor division 2. These two statements are related, and these are basically properties coming from the fact that heaps are complete binary trees. Now, a min heap has an additional property that the value of every parent node is less than or equal to both or say any of its children, because it's possible that it may have only one child, but then the value must be smaller than that child, right? So it should be both or let's say any of its children. An important implication of this, and think through this, is that the root node in a min heap will always be the smallest item in the list. A very, very, very important point. Conversely, we can also talk of something called a max heap, where the value of every parent node is greater than or equal to any of its children. So both in case two children. If it's one child, then the value of the parent node must be greater than the value of that child. If that happens, then we have a max heap. And think about it again. This implies that the root node in a max heap will always have the largest item. Now, just for a moment, go back to where we started all of this discussion. Remember, we talked about priority queue problems where we have dynamic data, but we are interested in keeping track of the minima or the maxima, so highest priority perhaps, right? And you can clearly see heaps are probably going to help us because through the process of, let's say, creating a heap, we realize that the minimum value or the maximum value ends up being at the root. So that's sort of the intuition behind where we are going. Obviously, this will become more and more clear as we move forward. Just one small note that we are going to deal only with min heaps here, not because max heaps are not important, but the reason is in Python, and we'll see this later, by default, we create only min heaps. So we'll, in fact, as a next lesson, we'll see how we can, use the min heap structure itself to create a max heap. But that's for later. For now, let's just limit ourselves to min heaps. Let's see some examples of what would be min heaps and what would not be min heaps so that it becomes clear. So let's look at example number 1. Let's say I have this list over here. Now the values here are 1, 5, 40 and so on and so forth. Remember, I impose a complete binary tree on this. The structure that emerges is as shown here. Rule has been followed exactly like we were talking earlier, top to bottom, left to right. So 1, 5, 40, 14, 7, 58, 61. 71, 18, 11, 15, 60, 72, 78, 89. So look at this. I'm going in this direction, but I'm filling up this tree from top to bottom, left to right. So that is a complete tree. In fact, in this case, it's also a perfect tree. You notice that look at any parent. So for example, this node here, 0th node, that's a parent node. That's a root node also. Its children are at 2i plus 1, 2i plus 2. So 1 and 2, the value of that children. Okay, look, value here is 1, value here is 5, value here is 40. So this node satisfies, let's say, the min heap property. Let's look at this node. Value is 5, value is 14, 7. Clearly this also satisfies. So does this, and so do all of these nodes. So look at just this one, for example, 61, this is 78, this is 89. So this is a min heap because, like I said, every parent satisfies the min heap property. Each one must satisfy. Now, the important thing to realize is that the complete binary tree structure could have been imposed on any list, but whether the list represents a heap or not depends on the values that are stored in this heap. And that's a very, very important point. that look, the values in the list determine whether we have a heap or not. Let's look at one more example. This time round, not a perfect tree, but never mind. It's a complete tree nonetheless because we are filling from left to right, top to bottom. So 1, 5, 40. Notice I just take this list and keep filling this up. In the last level, I have 71, 18, 11, 15, 60, 58, nothing beyond that. Perfectly fine. This is a heap, a min heap, because notice the value at root node is smaller than these two. Value at this root is smaller than value this node is smaller than its children, and so on and so forth, right? So let's say if I had only one child over here, if the value was, let's say, 64, then I still have a heap. Again, like I said, the fact that something is a heap or not depends on the values that are stored in the list. And we see that by imposing this tree structure. Before wrapping this up, let's look at something that is not a min heap and why it is not. Where does the failure happen, right? Now, this list here, 1, 5, 11, 14, 7, 18, 10 is not a min heap. Let's see why. Because, so for example, at the root node, it's all okay. So 1 is smaller than 5. 1 is smaller than 11. This node is also fine. 5 is less than 14. 5 is less than 7. However, there's a problem at this node. 11 is more than 10. This is not a heap. But just take an interesting observation here. We'll see this later more carefully. If I were to swap, let's say 10 and 11, in fact, which means that basically interchange these two items, in fact, the resulting list will indeed be a heap, right? So this is not a heap. Let's look at one more example. This example. Now, this is not a min heap because there are two violations here. In fact, I marked them in red. This parent here is bigger than the child. That's not allowed. This parent here is also bigger than both its children. So that's also not allowed. Because 7 here and 5 and 3, although every other node was satisfying the min heap property, but this is not a min heap. Now, before wrapping this up, let me give you a small puzzle. Do think about it. Do pause this video right here and get your answer before moving further. Is this list a heap? Notice here we have 5, we have 5 again, we have 5 again. Is this a heap? Now, the way we determine this answer is, remember, back to basics, just apply the rule. Every parent must be less than or equal to the children. So in this case, well, 1 is definitely less than 5 and 10. This 5 is less than or equal to its children, which is 14 and 5. This 5 here is also less than or equal to its children, which is 5 and 7 respectively. So yes, indeed, this is a heap. Now, very interesting observation to make here that look, lists which are heaps may not be fully sorted. However, as you're seeing in all these examples, the smallest number, because we're looking at min heaps, is always at the root, and that just follows from the fact that look, we have arranged it. The way we have done it is children are bigger than the parents, right? The min heap property, yeah, example, right? So this is a heap. This is a heap. Always the smallest item comes on top, right? Like I said, we will talk more and more about this. I hope you found this interesting. Do think about it, and absolutely happy to discuss if you have any questions. As always, at YByte, we try to come up with clean, simple explanations, examples, so that we can understand what's going on. Do look at our website, www.ybyte.in, and forever enjoy programming. Take care. Thank you so much. Bye-bye.